Hello friends, welcome to our channel. Let's look at problem 3478. Choose key elements with maximum sum. In this video, we're going to use heap and the two-pointer sliding window method to address this problem. So here, let me first go over the statement of the problem. So here we are given two integer arrays, nums1 and nums2. So they have the same length. And also we are given a positive integer key. So we want to do the following. Then for each index I, perform the following. So we find all the indices g where nums1 g is less than or equal to strictly less than. So this is the important, less than nums r1 I. So if you change this to less than or equal, the problem will be dramatically simpler. So we want to choose at most key values of nums2, right? nums2g at these indices to maximize the total sum. So we want to return an array answer of size n, where answer I represents a result for the corresponding index I. So that's the problem statement. So here, let me first look at the length, right? The length can be as long as 10 to the power 5. So in other words, we need to think of term complexity. Both numbers are positive numbers, and the key is consistent with the length because it's less than or equal to m, right? So with that said, let's look at example 1. So actually, if you want to find all the indices corresponding to smaller numbers, you can sort the nums1 with respect to the index. For example, if I sort these numbers from small to large, and also I get the index information, we get something like this. Right, so at index 2, it's corresponding to 1, so it's smallest. And then at index 1 is 2, right? At index 4 is 3. And then at index 0 is 4. And index 3 is 5. Then for each index, see, for example, index 4. So we know that to the left, the numbers are less than or equal to, right? So, but here, what we want to find is numbers strictly less than. Right, so if we want to find less than or equal to, then I just want to look at the left side. That's okay, right? Then I just need to rearrange nums2 according to those indices, and then I get if I have key, I just choose key. If I do not have key, I just choose all the ones to the left. So, but not here is not the case. Example 1 actually isolated this situation, which gives us a completely strictly increasing, in other words, all the elements in nums1 are different. But in example 2, we get another extreme, right? The numbers are exactly the same, just only one unique element. So these are the two extremes. But in reality, for a representative example, they should have both. Some numbers may just appear once, and the others may several times, right? So here, if we look at index 2, right? For index 2, there's nothing to the left. So index 2 will correspond to 0, right? This is the return for index 2. For index 1, so I know that index 2 is less than, right? For index 2, this corresponds to, let's see, for index 1 is corresponding to this one. So you get 30. For index 4, right? There are two numbers in the left. Corresponding to these three numbers, but I can only choose 2, not so this is the 4, right? Let me see. So here, for index 4, there are 2 in the left, right? 2, 1. So for index 2, 4, there are 2. So therefore, you can choose the 2 because the key here is 2, 50. For index 0. So there are 3 and to the left. So this 3. But you can choose 30 and 50. So total you get 80, right? So this is for index 0. And for, so this is the index 3. Let's see, for index 3, yeah, same. For index 4, because you also include 30 and 50, you choose the 2. For index 3, so you get to the left, that is, let's see, for index 3, where's 3? Let me see. For index 3, all the indices are to the left. Again, you can choose this 40. So here, let me walk it through again. So I guess I got confused. So for index 2, no left, so you get 0. For index 1, you have just 1 left, so you get 30. For index 4, you get 2 left. So you get 2 left, and then you are going to get these 2 numbers, sum, right? So then for index 0, you have 3 and to the left. So, but you can choose the 2 largest one, that's 30 and 80. And for index 3, again, you can choose 30 and 50. So you get, this is index 3, right? So this is index 0. Both are 80s. So this is the one. And for example 2, so both are 2s. So for each number, there's no smaller ones, right? So therefore, you just get all zeros. That's the second one. So in order to consider this, we can use 2-pointer sliding window method. For each index, for example here, so we can get a left pointer. And then once we meet something equal, then it means that from this left index to the current index, all the elements are equal, because it cannot be larger, right? So we just break. So now let's look at the coding. So first, I'm going to get the length of nums1. So this is also the length of nums2. Then I initialize a result 0 times m. The final state of this list is what we want to return. So we can write something like this. And then we can first, I'm going to get this information. So let's say sort it. And then what we can do is we sort the element and the corresponding index for iy in enumerate. So we sort nums1, right? And then once we get this, so we can initialize a heap. The heap help us to choose the key largest elements if possible. So then what we are going to do is this. So we don't need to explicitly get this list, actually, if you look at code. So here, let me get a sum. So here, notice that I'm using a bar, because sum is itself a function in Python, built-in function. So let's get a left pointer, that is 0. And then we are going to iterate through this for I in range m. So we can look at the current index. So we'll see the current index will be ref at I at index 1, right? Then, so basically we check well j is less than this index. So first we get the previous index. The previous index would be ref and j and 0. So not 0, so it's 1, right? Ref j. So now we have this one. So what we want to check is the value at this one. So if index at this j and the corresponding number equals this number, ref at I 0. So this means that it's not smaller, right? So they just break. So that's the one. And otherwise, if at the this index j, so the corresponding number is smaller. So what we are going to do is this: heap push. We are going to push this elements. So it's nums2, right? At index previous index, right? And then the sum is incremented by this number, right? So it's nums2 and previous index. So this guarantees that we get all the numbers. And then we want to check another one. So we want to maintain the length of the heap to be at most key. If the heap length is greater than key, so we're going to do pop, right? So we're going to heap q heap pop. So from this heap, notice that so this line of code actually did two things. First, we pop this smallest element from the heap, and also we decrement, right? So decrement this. So then afterwards, so we can increment this g by 1. So pushing this pointer to the right. So then after this while loop, we are going to get the result for the current index, like here. That's why also it caused some confusion. So now what we do is this. Answer at the idx would be the current state of this number. And then we are going to return the result. So that's our full coding. Before we make any comments, let's first do a test. Wrong number. So let's see what's the problem. So nums 2. So sum is incremented by nums 2, and we got the current index, and then for j, so here not j is not less than this one, less than I, right? Yeah, it passes the two test cases. Now let's look at the generic case. Yeah, it passes all the generic cases. So with that said, let me make a comment. So here, first about the two examples. As I mentioned, the example 1 contains all unique elements, while example 2 contains just one unique element, and every element or as a set is just a single element. So that's the two extremes. So in reality, so we should have something in between. So because of this, and because of this assumption, where nums 1j is less than nums 1i. So because of this, we should have this while loop. So this is the one thing. So here, the second comment might be easier, extension or practice. So if I change this one, to be less than or equal to, yeah. Can you say quickly solve the problem? Because with this less than or equal to, the problem is simpler. So with this practice said, I guess that's it for the current video. Thank you for watching.